we're changing gears a little bit now towards the end of the course. This is work that I did with a student who was visiting me at Argonne National Laboratory for 2 summers, Dominic Young, and we worked on optimization problems of neural network constraints. So we were interested in solving problems that have special structure in them and maybe formulating them as mixed integer nonlinear optimization problems. So at the Department of Energy labs like Argonne National Laboratory, we're interested in solving really challenging, often multi-physics optimization problems. And in many times, those are problems that you can't necessarily formulate in modeling languages such as AMPL because they involve complex, often multi-physics simulations. So I write this here as an S of X. So S of X is some simulation package that you're calling. It could be Phoenix for solving partial differential equations, for example. And then around that, you have an optimization goal. You want to minimize a function, and you have some constraints. And often, not always, these simulations are computationally very expensive. So that means we're running, if you, for example, think of running a climate simulation, that would run on the biggest supercomputers of the world for hours. And so those are really expensive, computationally expensive simulations. But we still want to optimize over those things. And so I have 4 examples here. I'll just talk about 2 really quickly. The first one we worked on a little bit was the design of these concentrating solar plants. So what you see here, these are all little mirrors that reflect the sunlight to go to this tower, the top of this tower here. And there was a part, I think, in a James Bond movie where Bond was sort of tied up there and sort of had to get out of that. They don't do that anymore. Instead, they try to generate electricity with these concentrating solar power plants. What they do is they run a cycle of molten salt. So the table salt that you have on your table, they melt that to about 800 Fahrenheit, and they run this through a cycle, and then there's a second cycle where you have a turbine. You can sort of see some small buildings here in the center where you have a steam cycle and you generate electricity. What's really cool about this is that you can generate electricity even if it's cloudy. That's something you can't do with photovoltaics, the normal solar cells. In this case, you can actually store the salt. You can have storage containers of this molten salt, and you can store it and generate electricity when it's dark outside, for example. And so these power plants, we're sort of trying to find out how to build them in an optimal way. And the simulation here would be you lay down an array of these fields. You have a certain dimension of and size of your solar tower, and the dimensionality of the molten salt cycle that you're building, and you simulate forward in time, maybe over a year or 2-year horizon, what this plant will be doing. So the simulation packages that you can run, the simulation packages themselves will be doing some scheduling operations, there's uncertainty involved, and there's no way to differentiate through these. The second example I'm going to pick is also related to solar cells. This is a snapshot of an idea that people at Sandia National Lab had, where they want to build a sort of one-way mirror on top of photovoltaic cells. The idea is that you want sunlight to go in, or photons to go in, but not to come back out. If you can manage to do that, if you can trap all the photons, then you can potentially build a very effective solar cell. So you don't want the sunlight to be reflected, you want it to be trapped inside the solar cell. And to do this, they're designing these ZIA elements. So those are, that's a space-filling curve design, or space-filling blocks here that you have. And on each side of these blocks, you can print these nanomaterials, which is sort of little gold particles that you're printing on the side. And you have a finite number of angles that you can rotate them with and how you can arrange them. And you're then solving a Maxwell's equation to simulate the sort of solar beams, sunbeams going through here, while you're rearranging, in a sense, optimally trying to rearrange what this looks like. And so there's a very complex simulation that goes into it. Similar things happen for studying the brain or subsurface flow. So you're interested in making sure that contaminated sites don't contaminate the rivers, for example, in the Pacific Northwest. Very expensive simulations. So it would be hard to optimize over these. And what people have started to do is we've started to build machine learning models, so deep neural networks or other things that are surrogates, cheaper and easier to evaluate surrogates of these complex simulations. So rather than running the complex simulation, you just evaluate this cheap surrogate that you trained on some training data. And this has been applied widely, so in the design of new materials. There is a Center for Nanoscale Materials at Argonne, which is doing this, in the design of energy systems, or in oil well scheduling. And so I'm going to look at optimization problems that have some kind of machine learning surrogate that approximates our nonlinear simulation. So the nonlinear simulation that I had earlier is approximated somehow, and I'm assuming that I'm given this surrogate and I can just optimize over this surrogate now. So I'm going to study optimization problems which have this form. I'm minimizing an objective function that depends on my surrogate and maybe the variables that I have, and I have some nonlinear constraints. I'll give you an example in a moment. And these variables, some of these variables could be integer variables. That's what makes it interesting. And we're also going to, in the second half, going to talk about a formulation for this problem. So one way of building these surrogates would be through a neural network. And so on the right here, I picked a picture again of the internet, which is a depiction of a neural network. So the way to think about this is that you have an input layer, and in the input layer you encode the input, the sort of signal that goes into the neural network. On the output layer, you encode the output. So for example, the input could be an image, in which case there would be, depending on the size of the image, there would be per one input neuron, those are those round points here, per pixel. And the output could be a classifier that says this image is a certain digit, or it's a different digit, or it's a cat or a dog. That will be one of the ways of doing that. And the way these neural networks operate is that we have weighted edges that connect the neurons from one layer to another layer, and the weights are these matrices W that basically take the input from one layer, so the input from YL minus 1, you multiply this by this matrix, and you add some offset, and then you apply a simple nonlinear transformation, and that's sort of an activation function, and this is just the max function here, for example. So this is a pointwise max function that you would apply. And you can write then this a deep neural network as just a concatenation of more and more of these max functions. There's a zero missing here that you sort of apply. And in this talk, I'm going to assume that this deep neural network is given to me. So somebody has trained it, and I just want to optimize over this deep neural network. So the challenge is that, one, I have this rather weird-looking nonlinear function that's concatenated of all these max functions that I need to deal with, and I might have some integer variables as well in addition to that. Now, the training, this is just an aside. How would you train these neural networks? You're typically given data. So you're given some input data, xk, those are the yellow nodes here, and some classifier, ylk, that's the output. And then most methods would somehow try to minimize the data misfit between the classifier that you're given and what the neural network computes for you as a classifier, given the data. And so there's some kind of, it could be a least squares expression, there could be additional terms where you're regularizing, it could be a different loss function that you could be applying there. But conceptually, that's what you're doing to find these weights, is basically solve an optimization problem. So that's just a little aside. And once you have the weights, you can then plug in any value now, not just the values on which you trained, but any other value to predict what the outcome would be if you put that value, if you had that value here. And there's a lot of literature, and I'm simplifying this hugely. That goes into how to train the neural networks, things like cross-validation. So you would train and then you would check on a set of data that you haven't trained on, whether this was a good training. The optimization needs, these sums here are probably very large sums, so that you often have a lot of training data, millions or billions of examples, and so you need to do some kind of sampling to get good and efficient methods. But we're not going to worry about that. Instead, I'm going to look at one particular example and then tell you how we're working on this. So the goal is to do optimization with these machine learning surrogates that are plugged into our functions that make these functions really complicated. And ideally, I want to leverage everything I know about nonlinear optimization or mixed integer nonlinear optimization so that I don't reinvent anything. There's obviously some non-differentiability and non-convexity that I need to handle because my functions is this concatenation of these max functions, so I have to be a little bit careful there. That's a non-smooth function. And what I'm going to look at in the remainder is, for this machine learning model, I'm going to use a deep neural network. So like the one that I just showed you. But you can have other machine learning surrogates, and then you apply different tricks. And so what we did was we looked at the design and control of a combustion engine. And so typically to simulate this, that requires a lot of computational power. And we got a neural network that was changed by a couple of colleagues of us that trained and provided some good approximation properties. And the goal that we're interested in is minimizing the emission for a set of drives. So we want to save the planet, we want to reduce global warming, so we want to minimize the emissions of sort of two things that are emitted. Subject to, we have to have some trip profile that we need to satisfy, and we have constraints on the fuel injection, the revolutions per minute, and the compression ratio. And that actually turns out to be an integer variable. So one of the things is that the compression ratio in your engine is something that's prescribed by a sort of small set of integer values that you can choose. And so the deep neural network is basically a prediction. It predicts what the emissions are and what the torque is for a given input variables that we put in. And all this is time dependent, so I'm discretized time here, so I do this at different time steps over my trip that I'm taking. The torque constraint really means the car is moving, I'm moving forward, because if I didn't have that constraint, I would just not inject any fuel and not create any emissions. So I would just minimize these numbers here. Okay, so this is actually not such a difficult optimization problem anymore. There are really, depending on how long the trip is, there's really only 3 variables per trip that I want to look at. And really there's only 2 decision variables, namely the fuel injection and the RPMs that I'm running at. And then the compression ratio is sort of one that's constant over the trip. So that's like the design of the engine. It's a very simple model that I'm looking at. So we looked at the neural networks and sort of what the prediction is. And so here's sort of contours modeling for different values of fuel mass or injection and revolutions per minute. We're modeling what this is the NO emissions, and this is the CO emissions, I think, on the right. And so we want the emissions to be as low as possible, so we want them in the low blue values there. But if I'm operating on those values, then I might not be able to complete my trip. So one of the things to look at is that these functions are very non-convex. And then, so when you look at the contour plots that we did, they're sort of highly non-convex functions there, and they're also non-smooth functions. So there may be many local minimizers. And I'm not going to tell you how to handle the non-convexity. I don't know how to do that. I can tell you how to handle the non-smoothness. That's as far as we got. Okay, so there's a second application that we're looking at, and that's an adversarial attack generation problem. And you might have seen that. The question here is, you have training data. For example, there's this well-known set of MNIST training data where you have a lot of images of the digits from 0 to 9, and you want to train a classifier that correctly identifies a digit for something that is not in the training data. And so those are handwritten digits that come from the Postal Service, I think, in the United States. And it's been observed that by just putting a small number of, or perturbing a small number of pixels, you can often get it to misclassify in image. And so we were interested in finding a misclassification or setting an adversarial attack problem. So our classifier would sort of identify the correct problem, and we want to find an X, basically, that gives us a complete misclassification, where Z is a sort of binary actor here. So for this adversarial attack problem, that's our second application. This is a bit of details that goes into what the neural network looks like. There's a final layer, is a soft max function that basically provides the probability of classifying, how to classify the problem correctly. And this has also been looked at by Fischetti and one of his students to sort of optimally design these adversarial attacks. So we're trying to perturb the digits to get them to make the wrong decision. Okay, so I'll talk a little bit in the remainder how you can embed these ReLU or deep neural networks in optimization problems. And one way of doing this is to make use of the packages that are out there, such as TensorFlow and PyTorch. And so Dominic, he actually went to the trouble of writing an extension to IPOpt that allows us to directly import, in this case, I think it's from PyTorch, the gradients and the function values from PyTorch. And so there's a way of expressing these functions in a way that becomes that is efficient. And the caveat there was that if you do that in traditional modeling languages, then that's not very efficient. The automatic differentiation isn't as efficient as it would be as the automatic differentiation that takes advantage of the fact that these are neural networks. So the automatic differentiation techniques that are implemented in TensorFlow and PyTorch are very advanced and very fast. And so we wanted to take advantage of those. And so he defined some macros that allowed us to basically call the neural networks directly from PyTorch while we're solving the optimization problem, and also to get gradients. And so we're getting gradients and function values from PyTorch, and we import them into our nonlinear optimization solver, sort of doing that through JUMP rather than through AMPL. You can also do this in AMPL, but it's a little bit harder maybe. And we're using this popular activation function, this max function. So the ReLU function is simply the pointwise max of 0 and this linear affine function that you've trained on. And so here's a sort of picture of what the max looks like of 0 over x. And it has been speculated that really this is not an issue. So people have solved that people have trained deep neural networks with these max functions in there for years, for decades certainly, and there doesn't seem to be an issue. They give very good classification results, and to some extent that's the industry standard. However, when we ran this, so we set up an optimization problem like this. We had our automatic differentiation and the evaluation of these gradients set up, and we called a solver. This was IPOpt, and this is the result that we got. So let me show you what this is for a moment. So it's we plotted over the number of iterations. We plotted, first of all, the objective function value. So that looks okay. There's a result there at -50, which is great. And we also plotted the dual and primal infeasibility. And so what you see here is that the primal infeasibility, so that's the blue line here, that goes down to maybe 10 to the -5 or so. But the dual infeasibility, and that is that's the norm of the gradient of the Lagrangian. So dual infeasibility, that's the norm of the gradient of the Lagrangian with respect to x. That is bounded away from 0. And in this plot, it's sort of, you can see it's sort of greater or equal to something like 5, which is greater than 0. So you're doing 3,000 iterations, and this dual infeasibility, this KKT error that should be 0, is bounded away from 0. 3,000 iterations is a lot. I could have taken another solver here. We took IPOP because it has some nice features, but any other solver would give you the same result, or very similar looking result. And so we looked at this a little bit, and this is sort of not surprising. So what we saw was that the step size over the iterations actually converged to 0. And the reason for that is that we can also measure, but we're evaluating the activation function, the neural network. We can measure how far away we are from this kink. So we measure the distance to the discontinuity. So the max function has this discontinuity at 0. And what we're measuring in this plot is how far away we are from the kink, either on the left or the right of the kink. We measure the distance to the kink. And what you can see in the picture is that initially we're far away from a kink, and then eventually on the sort of last 1,500 iterations or so, we just get closer and closer to the kink. And it looks like we're getting stuck because we're not reducing this dual infeasibility. And Dominic then also plotted in just 2 variables what the non-smooth areas look like. So on the left here, you see a 2-layer network. So that's not a very deep neural network. 2 layers is not deep at all. That's very shallow. And the blue line and the green line correspond to the areas of discontinuity that you see in these 2 variables, in the fuel injection and revolutions per minute. So on those 2 variables, when you project it down this neural network, you see this sort of lines of discontinuity. And this gets worse if you add another layer. So now you add a 3rd layer, and you can see there's lots of lines of discontinuity, and some of these lines are actually overlapping. And this is sort of looking at neuron 27 and how far away we are from the hyperplane. You can see that the distance to discontinuity gets smaller and smaller. So what looks likely what we're happening is that we would like to take a step, but we're sort of bounded by bouncing into these discontinuities there. Okay, so there's an alternative function that we could take, and that's called the swish function. And it's sort of developed at Google. It's named after the swish that you have from Nike. And so it approximates the ReLU function that you have here. And if you take beta large enough, then it becomes a very good approximation of the ReLU function. And so the swish function is a smooth function. So that's a nicer function. The classification is not quite as good, but it has nice smoothness properties. And you can show that the swish function parameterized in beta approximates the ReLU function as beta goes to 0. So when we use this function, that's what happens with the solver on the right. So on the left, you see the bad convergence for the ReLU function. The dual infeasibility or KKT error was bounded away from 0 here. It's sort of above 10. That's the orange line. And the step size converges to 0, so you really get stuck. While on the right-hand side, you see beautiful and nice convergence. So both the primal and dual infeasibility converge towards 0. The values here are much, much better, 10 to the 7 to 10 to the minus 13. And you only take about 25 iterations. And so IPOpt, if you give it a smooth problem, it works great. And that's what we expect. So the failure is really due to this non-smooth behavior that we have. And there was a nice paper that came out in 2020 by Bolton and Powells, where they looked at the probability of hitting a non-smooth point. So they did this little experiment where they designed, randomly chose 1,000 sets of weights and offsets for a neural network. So they didn't train a neural network, they just randomly generated 1,000 neural networks. And then depending on the number of layers and the size of each layer, so the number of layers on the x-axis, the size of each layer on the y-axis, they evaluated each neural network, each of those 1,000 neural networks at 1,000 points, and they asked themselves, am I at a point that's discontinuous or not? And it turns out that the probability that you're at a discontinuous point is actually non-zero. So 1 or white is where it's non-zero. And so for neural networks that have a lot of layers that are maybe very narrow, you get this probability that it's almost 1 that you hit a point of discontinuity. If you have very few layers and the layers are very fat, then you're likely not to hit one of those points. And so the insight here is that, or the point here is that the point at which the discontinuity happens, that point is a point of measure 0. So if you sampled randomly on this image here, you need to sample a lot of points before you get even close to this point. So the 5 points that I just sampled randomly, you're always away from discontinuity. But you're now concatenating these max functions, and because you're concatenating them in this special way, you get this behavior that if you have a lot of layers, and so you're doing a lot of concatenations of these max functions, then you suddenly start to see non-zero probability of encountering, of landing at this point here. So the theory tells us it's a set of measure 0. In practice, it's not. And that's sort of a really nice result. And what this result tells us is that we shouldn't really be using this ReLU function if we want to do smooth optimization, because we get into this behavior where the algorithms just don't converge. So 3,000 versus 30 iterations. Okay, so here are my conclusions. I have 3 sets of conclusions. Deep neural networks with ReLU activation functions are non-smooth. They are really non-smooth. Believe me, they are non-smooth. And so in the next lecture after lunch, I'll tell you how to resolve this using integer optimization. So we'll go back to integer optimization after lunch, and I'll give you one trick on how to solve these problems using integer variables. In fact, I'll show you 2 different ways of formulating these problems. But the key observation is this is the picture that you should have in mind when you want to do optimization over machine learning surrogates. You have to be careful. You need to be mindful of the fact that you could run into issues there. And you will typically see these issues when you plot the dual infeasibility. So when you look at KKT error and that's not going down to 0, then you're probably fighting against the non-smoothness of these problems.
Can you go to slide application 1?
Application 1. This one? Okay. How did I formulate which? This one here. Oh, okay. I understand what you mean. Yes. So we have emissions, which are a function of time. And so there's this NO of t and CO of t. And let us assume I didn't put it here, that they're both non-negative. That's actually a constraint that we forgot. And then what we're interested in is we want to minimize, we want to integrate. So I draw a picture. Let's draw a picture first. So over my time horizon, as I'm running my engine, there's some emissions that come out of here. So this could be my NO of T. And then I have my other emissions, CO of T. And what I'm interested in is over the whole trip from 0 to capital T, I want to minimize the integral. I want to make sure that, so this is like, so this is instantaneous emission, what comes out, but I want to minimize the tons of carbon that I put into the air, for example. So then we formulate this as the integral from 0 to capital T, NO of T plus CO of T dt. And this integral, one way to approximate this integral, a very crude way of approximating the integral, is to look at the value at time t and then multiply by the time step, by the discretization interval. So what I've done is I've taken a finite number of time steps here. This would be delta t, and then in each interval, I look at, for example, if I look at the midpoint, I replace my integral by sort of the summation of that I get at the midpoint, maybe. Something like this. So very simple, and I just sum up these values. Does that make sense? Oh, lambda. Lambda is a great question. Lambda is a parameter that allows me to trade off between the two. So I have a lambda here, and lambda is between 0 and 1. So I can trade off these two emissions, and I think we just set it to 1, I think. So we were just because it might reflect the fact that some emissions are more harmful to the atmosphere than others. So you could put that, you can model that in your model, for example, the lambda. Yeah.
We don't know the GIAN here.
We don't know the. So we do know the deep neural network. So I'm assuming that these guys there, Prasanna and Ashish, have given me a deep neural network. This is the deep neural network that I'm given. So I'm not training the neural network. I have something that somebody has given me that I trust.
So you use TensorFlow to calculate the derivative.
Yeah. You generate, you have it generated, you use that, and now you're using that neural network, the TensorFlow network, yeah. That's the plan. Yeah.
So it means that we are just using the response variable, the response value that we are getting based on the FT, RT, and C. How this embedding is going on between optimization model and this network?
Okay, so I've trained my neural networks on some data that I have for F and R and C, but I don't have data everywhere. And so I now let my variables roam free to find new values. So the way to think of this is that if I have two values, R of t and F of t, then my training data corresponds to some discrete set of points at which I know what the torque is and other values. But now when I'm doing my optimization, I want to drive my car maybe in a different way. Maybe I want to evaluate it here. And I don't have any data there. So I'm using the neural network to predict what the value should be at this point.
And that predicted value will be used as a constraint that we have.
Correct. So that I put the green star into this equation, and then that predicts what the output is. And then and so now I'm trying to minimize this output. So I'm sort of going backwards. I need to find I need to move this x around somewhere to find values so that I minimize my objective function. That's the plan.
If we do this operation separately, like for instance, I am predicting this value
Yeah.
of n over c1 dot.
Yeah.
And now I am putting that value into this formulation. So how it would be different from that formulation? Like not embedding DNA in here. Just I am using the prediction of this.
Okay. Then the question is, how do I change f and r? So these are the variables over which I'm optimizing, the f, r, and c, and if I just plug in these values for a particular value of f and r, then it doesn't tell me how to change it. So what I really want is I want gradients of this DNN with respect to f and r. Okay, this is great questions. Thank you.